Now let us see some more exercise questions. That is, complete each synthesis by giving missing starting material, reagent or product. And the first compound given is ethyl benzene. Now permanganate oxidation, we use alkali gavage, so alkaline gamma of run heat. Now what is happening is here that the CH3 group is completely converted to CO2 and H2O. And this CH2 is completely oxidized to COOH. Actually, the medium is alkaline, potassium hydroxide. So we get COOH. Then we can acidify this and get COOH. Now, what will be the length of this chain? The carbon directly bonded to the benzene ring will be oxidized only to COH, not oxidized to carbon dioxide, because of the stability of this benzene ring due to resonance. So what will be the chain length? The carbon to which the benzene ring is directly connected will be oxidized only to COOH, and all other carbons are oxidized to CO2. Now benzaldehyde with the semi-carbazide, simple reaction, oxygen and hydrogen combined with water, combined to form water, and we get CH double bond NNHCONS2. Now it's a ketone and aldehyde group is also present. Now reaction with the silver amine positive ion, that is Tollens reagents, ammoniacal silver nitrate solution in which this amine complex is present. So it is a redox reaction. The CHO group alone reacts, CO group is intact. CHO is converted to COO negative and the positive ion is ammonium ion. And the silver amine complex is reduced to metallic silver, which is observed as a silver mirror that you have seen earlier. Now how will you obtain this molecule from a starting compound? During ozonolysis, addition of ozone followed by hydrolysis. Now you remove this oxygen and write another same structure on the side. Then you get this one. On ozonolysis, a double bond breaks completely and two oxygen atoms are added. The valency of oxygen is 2, so these two valencies are united to oxygen and we get the starting compound like this. Now then benzaldehyde and propionaldehyde. The thing here is that benzaldehyde does not possess alpha hydrogen, and this compound propionaldehyde possesses one alpha hydrogen. And so an aldol type reaction can occur, and in aldol reaction the alpha H atom is actually getting connected to the carbonyl oxygen of the second aldehydic molecule, so that propionaldehyde splits into H as H positive connected to O. Here CO bond polarizes, ionizes like this, and the C becomes positive, and here H becomes positive and OH is formed, and the C negative gets connected to this carbon. We get an aldol like this. Now this is cyclohexanol, an alcohol on oxidation with the CrO3, we get the ketone. Now how will you convert this compound to an aldehyde group? One possibility is that reaction with the diborane followed by reaction with the alkaline hydrogen peroxide. We have seen this reaction earlier. We get a primary alcohol. So addition of water occurs, HOH addition, HOH addition. H is the positive part and OH is negative part. And during this addition, the anti-Marconi group is obeyed. That is, OH negative goes to the carbon containing, negative part of the adenine goes to the carbon containing the lowest number of carbon hydrogen atoms, alpha unsaturated carbon, the lowest number of hydrogen atoms connected to the unsaturated carbon. But anti-Markovnich's rule says that the negative part of the addendum goes to that carbon, unsaturated carbon connected to the largest number of such atoms. So we get a primary alcoholic group which on oxidation using pyridinium chlorochromate we get the aldehyde group. So that is one method of conversion of double bond CH2 to CH4, which is a peculiar reaction. Give a plausible explanation for each of the following. Cyclohexanone forms cyanohydrin in good yield, but 2,2,6-trimethyl cyclohexanone test. Now the structures of these compounds, you have to draw the structures of these compounds first. Carbon 1 is the carbonyl carbon, 2, not 2, there are 2 methyl groups, on 6 there is 1 methyl group. So this is 2,2,6-trimethyl cyclohexanone. Now here we can say evidently the methyl group sets at steric effect, this methyl exerts steric effect, so the nucleophile cannot come near the carbonyl carbon. So the reaction is prohibited due to steric effect, that is one reason. And again, a similar reason may be added, that is the plus effect of all these methyl groups directed towards the carbonyl carbon slightly diminishes the partial positive charge over carbon. So both these reasons, that is the steric effect and inductive effect, both decrease the approach of the nucleophile towards this carbon. Now a second question, there are 2 NS2 groups in semi-carboxylic. Only one is involved in the formation of semi-carbazone, and that we have seen this the reason for this earlier, that is due to resonance. The lone pair of electron is delocalized over the carbonyl carbon, so nitrogen gets a positive charge. So in the resonance hybrid, nitrogen is having partially positive charge, and this partially positive charge is charge of nitrogen makes the lone pair of nitrogen less available for donation to the carbonyl carbon. So the easily approachable lone pair is this one that will take part in the nucleophilic reaction with the carbonyl carbon. Then a problem, that is an organic compound containing 69.77% carbon and 11.63% hydrogen and the rest oxygen. So percentage of hydrogen, that is 100 minus 69.77 again minus 11.60, that will give 18.6. Now we can find out the empirical formula by dividing the percentages by the respective atomic numbers. 69.77 by 12 for carbon is to hydrogen is to oxygen. 11.63 by 1, that is atomic number of atomic mass of hydrogen is 1, atomic mass of carbon is 12, and atomic mass of oxygen is 16, 18.6 by 16. So we get the atomic ratio. And then take the least number and divide all these numbers by the least number. We get the ratio as 5:10:1, that is C:2H:2O is 5:10:1. So the empirical formula becomes C5H10O. And the empirical formula mass is 86, molecular mass is also 86. So that the molecular formula is C5H10O. Now, it does not reduce tolerance yield, so it is not an aldehyde. It forms bisulfide addition compound, so it is a ketone, phosphatate, forms iodoform, hence CH3CO group is present. On vigorous oxidation, that is important point, it gives ethanoic acid and propanoic acid. Ethanoic acid is CH3COOH, propanoic acid is CH3CH2COOH. Now, a ketone is a methyl ketone CH3CO because iodoform test is given. Then connected to a carbon chain CH2, CH2, CH3, that may be the formula. Now, such a ketone, on oxidation, the carbonyl group makes company with the smallest alkyl group, that is CH3. So that this carbon is oxidized to COOH. And this CS2 methylene group, it is active. Active methylene group means a CO group is adjacent to a CH2 group. There is a particular type of polymerization reaction where there is chance for a removal of H as H positive. This bond will be shifting. O negative, H positive. So polymerization reaction can occur. COH, double bond C and so on. Both these hydrogens are active in the sense it may be easily reacted upon by the oxidizing agent, so that carbon is converted to a carbonyl group. Then oxidation, if the reagent system is alkaline KMnO4, it is ionized oxygen plus a molecule of water. We have seen this reaction earlier. It may be considered as a system of two OH groups. This bond breaks due to repulsion between these carbonyl groups, because O negative and O negative, C positive and O negative, delta C positive and delta O negative for oxygen. So here also delta negative and delta positive, these two can repel each other, so that this bond will be eliminated. So easily reacted upon by alkaline KMnO4. Two OH groups are getting added, COOH and COH. So we get CH3COH and CH2CH2COH. So that is the reaction here. So the compound may be CH3, CO, CH2, CH2, CH3. That is the inference. CH3, CO, CH2, CH2, CH3. And this is pentan 2-1. That is it. Now coming to another topic, that is carboxylic acids, general formula RCOOH. Now the suffix oic acid is used for naming the system. If it is CH3COH, you number the carbon atoms starting from the carboxylic carbon 1, 2. So the acid group is given preference. You number the carbon of the COH group as carbon 1 and then second carbon. The parent contains 2 carbon atoms and the parent is ethene. Now you name it as ethene plus oic acid, remove E and connect these to ethane oic acid. So that is the method of naming, nomenclature. The carbonyl carbon in carboxylic acid is less electrophilic, and that is again due to resonance. So for most of the questions in organic chemistry, the simple answer is due to resonance. Here the lone pair of oxygen atom is given for bond formation. The valency of this carbon increases, so this CO bond polarizes in this direction, and we get a canonical structure. And since there is pi bond character of this bond in the resonance hybrids, the carbon atom will have more electron density around it, so that it is less having lesser positive charge, less electrophilic in character. Now carboxylic acid is acidic. Why? Because the carboxylate ion is more resonance stabilized than the pre-carboxylic acid. In pre-carboxylic acid there is charge separation, which will make the structure, canonical structure, unstable, whereas in carboxylate ion there is only one charge, so there is no interaction between, repulsion or attraction between charges, because only one charge is there, and these two structures are equivalent, in the sense similar. So it is something like the structures of benzene. Both the structures of benzene are similar, so they will contribute equally to the resonance hybrid. And again the negative charge is over an electronegative atom. Now carboxylic acids are more acidic than phenols. The answer to this question is that in phenoxide ion, phenol is acidic because phenoxide ion is more resonance stabilized than pre-phenol. In phenoxide ion, the less electronegative carbon atom carries negative charge in most of the canonical structures, whereas in the carboxylate ion, the negative charge is carried by the more electronegative oxygen atom. So there is more contribution to the resonance hybrid from the part of carboxylate ion rather than the canonical structures of phenoxide ion. So we say phenoxide ion is less resonance stabilized than carboxylate ion. Now coming to the preparations of acids method A, that is oxidation of a primary alcohol using alkaline K1O4 followed by acidification. RCH2OH, oxidation gives RCOOH. Now acidified potassium dichromate or chromium trioxide in sulfuric acid may be used. HCl is avoided due to its oxidation to chlorine. Now toluene C6H5CH3 benzaldehyde and C6H5CH2OH benzyl alcohol etc. oxidized by alkaline K1O4 to benzoic acid. So that is a method of separation of benzoic acid. Then next method is hydrolysis of amides and cyanides in acid or alkaline medium. Now the easy way to understand this reaction is you break all the bonds, triple bond. All the three bonds are broken. So for each bond you add one HOH. So 3 HOH, 3 OH groups connected to this carbon, 3 H atoms connected to nitrogen. Alkaline medium, if the medium is alkaline, we get ammonia as the product. And 3 OH groups connected to the same carbon makes the structure unstable. 1 OH is removed along with H as a molecule of water. So we get double bond between these two atoms. This carbon to valency, oxygen with its valency because OH bond is getting broken. So C double bond O, then OH. So this is unstable and we get RCOH. And if it is amide, then again the single bond is broken. A molecule of HOH is added because nitrogen is more electronegative than carbon, so that nitrogen gets the negative charge and H positive gets connected to NS2, we get ammonia. In alkaline medium, free ammonia is obtained and RCOH is formed. If the medium is acidic, we get the ammonium salt. So cyanides on hydrolysis can give first an amide and then the amide is getting converted to hydrolyzed to the acid. So detailed mechanism for cyanide hydrolysis I have given in previous videos. You may refer. Now then, from Grignard reagents, see carbon dioxide molecule can add on Grignard reagents. See, one of the carbonyl groups should be ionizing like C positive and O negative. RMGX ionizes as R negative and MGX positive. Now here X has got no role in this reaction because this reaction is conducted in either medium and either it's a non-polar solvent. So removal of X as X negative is impossible in this medium. Now R part combines with C and MgX combines with O. So RC double bond O, MgX is formed, which on hydrolysis OH, MgOH, H, RCOH is formed. So that is conversion of Grignard reagent into carboxylic acid. Now the derivatives of acids are there. Acid chloride is a derivative of an acid. Acid anhydride is a derivative of acid. Esters are derivatives of acids. All these compounds on hydrolysis can give the corresponding carboxylic acid. So RCOCl is an acid chloride. The CCl bond breaks, Cl is negative, so H positive connects to it, and OH connects to positive carbon. So RCOOH and HCl, that's the product. If it is an ester, there is a group C double bond OO with two valencies connected to alkyl groups. The CO bond is getting broken and this oxygen becoming negative combines with H positive and this carbon becoming positive combines with the OH negative, we get RCOOH and ROH. Now acid anhydride, see acid anhydride is obtained by the reaction between two acid, COOA, of the same molecule, of course, or we can have mixed acid and hydrides in presence of phosphorus pentoxide, which is a dehydrating agent. An OH and H combine and we get RCOOCOR, RCOOCOR. Now, in hydrolysis, one of the CO bonds break, oxygen being electronegative combines with H positive, and carbon being electropositive combines with OH negative, RCOOH, and we get RCOOH. So two molecules of acid are formed, and that forms the preparation reactions of carboxylic acid. Now, in the next video, we shall see the reactions of acids. Thank you.